Lab 3, mass from motion. Problem, find the mass of a black hole using position versus time data recorded about a star, assumed to be orbiting it, solely under the black hole's gravitational force. The main result, the mass of the black hole was found to be 9.99 times the stellar mass orbiting it, or 1.99 times 10 to the 31 kilograms. When a known stellar mass travels on a known curved trajectory like an ellipse, it undergoes observable changes in position. Because of the curved motion it follows, changes in velocity and so changes in momentum can be calculated for a given position and time. We don't have to know what is causing the forces to observe their effects on motion. We know that by Newton's first law. We can define the sum of all forces acting on the mass to be F net, the net force. We can define the net force to be the calculated change in momentum using the momentum version of Newton's second law. If we assume that a single gravitational force acts on the mass, that force being essentially generated by a centrally positioned lone black hole, we can define the net force to be the gravitational force. Using Newton's law of gravitation, we can then calculate the unknown mass of the black hole. We can use computer graphics to show a simulation of the star's motion. To do this, we can plot the position of the star from the observed data and join it with a smooth curve. We can also compute the net force and the parallel and perpendicular components of the net force acting on the star. We can plot these and we can observe them on the graphics. These provide a visual indication of the magnitude and direction of the net forces acting on the star. I'm going to give you some assumptions and conditions. The file stardata.csv contains the observed x and y positions of the orbiting star. We assume the black hole is at the origin. We assume the gravitational force exerted by the black hole is the only force acting on the stellar mass. We are given the stellar mass as 1.98 times 10 to the 30 kilograms. The time interval between observations of the stellar position is 86,400 seconds, which is 1 day. The time starts at t equals 0. Here I'm showing some Python code. I've uploaded the code to YouTube and I commented it extensively, so I'll go quickly through this. You can look at that code if you're interested. And just show some calculations. This loop calculates the lists of x component of velocity and y component of velocity. We assume the time interval between observed positions is small enough so that the numerical approximation to the derivatives is accurate. I'm showing the net force calculated from the motion data. Basically, you find the velocity, initial and final, you subtract and divide by the time step. You get the velocity, which is the derivative with time of position. You do the same thing for momentum. And you find in the end you equate or at least define F net to be the derivative of momentum with time. Again, we're assuming that the time step is small, so the derivatives are an accurate approximation. This is how I calculate the mass of the black hole, basically using Newton's universal gravitational constant formula, just rearranging and solving for the black hole's mass. Here's a graphic of the Python that Python generated. You can see there that F net perpendicular was almost the same size and on top of F net, and F net parallel points away from slowing that the star is slowing down here. F net here, the yellow, points towards the black hole mass. What does it mean? What are the differences between F net and its components? And the derivative of momentum and its components, symbolized below here. We assume the numerical derivatives to be good approximations to the derivative of momentum and its parallel and perpendicular components. The net force or momentum are just a convenient way to represent the quantities. What is important are the vector quantities net force and momentum. Newton defined the net force in terms of the derivative of momentum. Momentum is conserved physical quantity. Although force is defined as a derivative of momentum, they are not the same thing. One way to think about it is that net force represents the cause for the change in momentum observed. In that way, the net force is an explanation for it. What if? The question, if you change a black hole for another black hole, can you tell that that's actually a different black hole using the same orbiting star with the same stellar mass? Not necessarily, because the only parameter we have to work with here is gravity. The black hole and the different one can have different rotational rates, but the same masses, then we wouldn't be able to tell them apart using the model presented here. Final thoughts, a problem. When we are modeling, we are assuming the black hole is fixed at the origin. This is only a good assumption if the black hole is much more massive than the star. Here we find the black hole is only 10 times greater than the star mass. This is ignored in this lab. We ought to think of what implications this has on the accuracy of the model. Thanks for viewing my lab report. Best wishes.